Okay, so we're going to move on to days 5 and 6, which we spent talking about probability and counting. So number 16 says, there are 4 candidates for a job. The members of the search committee will rank the 4 candidates from strongest to weakest. So if you're ranking candidates, order definitely matters because first is different than second. Steve and Laura are different than Laura and Steve, right? So how many different outcomes are possible? Order matters. That means this is a permutation. If we have 4 candidates and 4 slots, we have 4 options for whoever would be in first place. Then once we've placed someone, 3 options, then 2 options, then 1 option. So the total would be 4 factorial, which is 4 times 3 times 2 times 1. If we wanted to use the permutation formula, that would be 4 factorial divided by 4 minus 4 factorial, but that's just 4 factorial over 0 factorial, which is 4 factorial because 0 factorial is 1. What if there were 10 candidates to be ranked first through fourth? Well, now we have 10 possibilities for the first place, then 9, then 8, then 7. So 10 times 9 times 8 times 7 should give us the number. This is the same as, again, the permutation formula of 10 put into a string of length 4. So that should be simply 10 factorial over 6 factorial, but 10 factorial over 6 factorial is the same as 10 times 9 times 8 times 7. 17, in how many ways is it possible for the 19 of us to sit in a line? Sit in a line, can you tell the difference between Albin and then Malika and then John and then Chloe? And Malika, John, Albin, Chloe. Of course you can tell the difference between these two, so order matters when you're sitting things in a line. So that means it's a permutation of 19. That would just simply be 19 factorial. There are 8 greyhounds in a race. How many different orders of finish? First through third place, this looks again like a rank or an order, so order matters, are possible. Well, first through third, that should be simply 8 possibilities for first, 7 possibilities for second, and 6 possibilities for third. That would be 8 times 7 times 6, or 8 factorial divided by 5 factorial. Again, that's the permutation formula. Password for Gomer's email account consists of 5 characters chosen from the set GOMER. How many arrangements are possible if the password has no repeated characters? Well, again, order does matter here because this is different than OMERG. So that would be, well, you've got 5 options. You can't repeat, so then 4, then 3 times 2 times 1. So that would be simply 5 factorial. What about if the password may have repeated characters? Well, then you've got 5 and 5 and 5 and 5 and 5, so that would be 5 to the 5th power, right? So even more options there than 5 factorial. How many 5-element subsets are in the set S equals 2, 3, 4, 5, 6, 7, 8, 9? Now a subset has no order because 2, 3, and 4 is the same as 3, 2, and 4. We're not looking at strings, we're looking at subsets, so we really can't tell the difference with order. So we're really saying what is 1, 2, 3, 4, 5, 6, 7, there are 8 elements. What is 8 choose 5? That's what we're trying to do. We're trying to choose 5 things out of a total of 8. So this is a combination, and that should simply be 8 factorial over 5 factorial 3 factorial. Or I guess the formula is technically 8 factorial over 3 factorial 5 factorial, doesn't matter. That's 8 times 7 times 6 times 5 factorial over 5 factorial times 3 factorial, so we can divide the 5 factorials. 3 factorial is 6, so we can divide that, and we simply get 7 times 8, which is, oh boy, 48 plus 8, 56. So there are 56 5-element subsets of that set of 8 things. 22, do you think it's more appropriate to call a combination lock by its name or call it a permutation lock instead? Well, your question needs to be, does order matter? Well, certainly your combination 3, 2, 1 is different than 2, 3, 1. So order matters. Therefore, I would argue we should call it a permutation lock, right? Because order matters, and really what you're doing is different permutations of those numbers. 23, of course, that's kind of funny because we're combination, we mean something different in this case, but still, it's kind of an interesting question. 23, what is the probability that at least one of the 19 of us has the same birthday? Oh dear. I still haven't figured this one out or thought about it, so we may have to come back to that. Skip. $27, oh my goodness, that should be 24, but it says 27, whatever. It says, how many different 5-letter strings are there for the letters in the word zebra? Well, we've got 5 options for the first one, 4 options for the next, 3, 2, 1, that is simply 5 factorial options. A and B are 2 independent events in an experiment where this equals this and this equals this. This is the probability of A is 0.6 and the probability of A or B is, no, this is A and B, both is 0.2. Find the probability of B. Well, independent events, we know that P of A times P of B needs to be equal to P of A and B. That's the definition of independent events. So plugging things in, we get 0.6 times P of B is equal to 0.2. So the probability of getting B is simply 0.2 divided by 0.6. So the probability of B is equal to, I should be able to do this in my head. Let's see, that is going to be 1/3. Right, or 0.33. Man, we got a lot of problems here for probability, don't we? $29. A pair of 6-sided dice is tossed. Let A equal the sum is 7 and B equal 3 appears on at least one die. Use the space below to draw out the events A and B. The sum is 7. Well, the sum is 7 could be the first one is a 1 and the second one is a 6. We could have a 2 and a 5. We could have a 3 and a 4. We could also have a 4 and a 3, a 5 and a 2, or a 6 and a 1. So the sum is 7. This would be A right here. B, 3 appears on at least one die. It could be 3 followed by a 1 through 6. Or it could be a 3 on the second roll. Let's see, but we're doubling up here, so maybe I should just draw them out. So you could get a 3 and a 1, a 3 and a 2, a 3 and a 3, a 3 and a 4, a 3 and a 5, a 3 and a 6. Or you could get a 1 and a 3, a 2 and a 3. We already counted that one. A 4 and a 3, a 5 and a 3, and then a 6 and a 3. So that would be the event B. 3 appears on at least one die. Use the space below. Okay, we then calculate the probabilities in A through G. So the probability of A, well, what's our total sample space? 2 die, you have 36 options. That's 6 times 6. So in A, there's 1, 2, 3, 4, 5, 6. That would be a 6 out of 36 chance, which is 1 in 6 that you'll roll a 7. Probability of B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 36. Probability of A or B, or both. Well, that's equal to the probability of A plus the probability of B minus the probability of both. Probability of A is 1/6, probability of B is 11/36, and the probability of both, well, what do they have in common? These two right here. So the probability of both is 2 out of 36. So this would be 6 out of 36. 6 plus 11 is 17 minus 2 is 15 out of 36, which could be simplified, but I'll just leave that. Probability of A times the probability of B would simply be 1/6 times 11 out of 36, which is 11 out of 216. The probability of not A, well, that would just simply be 5 out of 6. That's the complement of A. Probability of A or B we already found to be 1 out of 18, or 2 out of 36. And this is not or, this is and, sorry. And the probability of A or not B, well, this should be the probability of A, okay, plus the probability of not B, minus the probability of A and not B. Okay, so the probability of A we said was 1/6. The probability of not B would be the complement of the probability of B, which is 11/36. So that would be 25/36. Wait, 25/36. And the probability of A and not B is, I can't